Third part is motivation first for studying the clusters in networks, and then we'll transition to this framework that we developed for studying the clusters and cluster analysis in networks. See, motivation, again, is shown using the social networks. I told you social networks are really central to many things that we are discussing here. Actors are people, and a tie exists if people know each other, or there can be all kinds of social networks. So some examples that you mentioned are just a few examples of the social networks, like friendship network or professional acquaintance network. There may be other social networks that you may not perceive initially as social networks. So for example, some of the typical examples that are used in the social network analysis for testing clustering algorithms would be something like co-authorship network. Then even football network, so for college football you have the nodes that represent the teams, and then the edges are representing the fact that two teams play each other, right, or are scheduled to play each other. And then there is a very nice clustering, natural clustering to the conferences. In fact, if you analyze this football graph, there may be some interesting things that you can observe. Let's say if I ask you, for example, if I have a college football schedule, right? So what is the maximum possible number of unbeaten teams that you can have at the end of the season? In college football, you have over 120 teams, right? But they usually play maybe 10 to 12 games, something like this. A very sparse graph, right? So if I ask you, can I design a schedule such that at the end of the season, I will have as few unbeaten teams as possible in the worst case? Can we have like a bound on this? So we can actually easily show that no matter how you schedule the games, in the worst case, you can have about 12 unbeaten teams at the end of the season. So if everything goes against the pollsters and so on, they may have to deal with like 12 unbeaten teams at the end of the season. Can you imagine? No matter how you schedule. In social networks, of course, we are looking for cohesive subgroups, right? Cohesive subgroups are closely knit or tightly knit groups in social networks, and social cohesion is used to explain and develop sociological theories. And normally you are looking for these large cohesive subgroups in social networks because they tend to play an important role in overall structural characteristics of the network. Let's say if you're looking at the tiny little cohesive subgroups, chances are it may be very powerful still. But usually these large cohesive subgroups, they intuitively can tell you more about the global structure of the network, right? So that's why we are typically looking at large cohesive subgroups, but generally we are interested in all of them, really. So because there may be some small ones that are very interesting as well, but then knowing the size of the largest one is still important because it kind of gives you a global bound on how large a cohesive subgroup of a certain type can be. So that's why we'll be focusing a lot on detecting this large or the largest possible cohesive subgroups in the networks, okay? And then what is a cohesive subgroup? There are many definitions which we are about to start talking about, but some of the common properties that you would want to see in a cohesive subgroup are familiarity. You want the degree within the group to be reasonably high. You want every member of the group to know a reasonably large number of members of the group, right? So for cohesion, familiarity should be significant, right? So then the second property you want to have is reachability, which in graph theoretic terms is represented by distance or diameter. Network science literature talking about a small world phenomenon, right? Typically, if you are to design a cohesive subgroup, right, so you want to make sure that these distances between nodes are short, relatively short. So, and this is easy reachability between the nodes within the subgroup, right? The third concept would be robustness. Robustness. What is robustness? It's typically the ability of the system to withstand targeted attacks, right? So with robustness, you are looking at your cohesive subgroup, and you want to make sure that the cohesive subgroup preserves its structure, even if some of the nodes or arcs are removed. And this is expressed by the concept of connectivity in graph theory. So essentially, connectivity is something that we'll talk about later. Connectivity is how many vertices you need to remove, the minimum number of vertices you need to remove in order to either disconnect the graph, to break it down into different connected components, or make it trivial. So let's say if I had a completely connected, like a complete graph, right, on n nodes, and the connectivity of a complete graph would be n minus 1, because I have to remove all but one nodes essentially to make the graph disconnected or trivial. If I'm talking about a tree is very fragile, right? So just removing one node already destroys the connectivity, so it's one connected. Yeah, that's something that is desirable to have in the cohesive subgroup, but that depends on the situation also, right? So for example, in transportation networks, not necessarily you have this property because it becomes too expensive, right? And then density is another characteristic. In real life networks, the density tends to be very low, right? So, but then if you're focusing on cohesive subgroups, if you're looking at clusters, you expect the density within clusters to be much higher than the overall density of the network, right? So that's why we had this clustering coefficient, and we said that, you know, the real life network tend to be more clustered because there are these local groups that have high edge density usually, all right? So the concept of local and global clustering is very closely related to that of edge density. Now, if you are to come up with a definition of a cluster that is perfect, what would you do? We want to have some of these properties here, right? So if I have a graph on n nodes, and I want all of these properties to be at their best, how would you build that cluster? So what would it be? A perfect cluster.
High familiarity, and then you would want a lower diameter.
Yeah, so we want, so the highest possible familiarity is what? When you have everybody is your friend, right? The lowest possible diameter, again, you have to have every single arc in the network, right? So the highest robustness, the same. The highest density. It's a complete graph, right? So you want to have every possible edge. So that's your perfect cluster. So like everything that could be connected is connected. We call this graph here, we call it a complete graph. But then if I just look at the set of nodes, the set of nodes of a complete graph is called a clique. All right, so this is a set of pairwise adjacent vertices. That's the definition. And then there is a very subtle difference, which linguistically maximal and maximum is probably the same thing, right? Maximal, maximum. Maximal is adjective, maximum is noun, but other than that, it's the same thing pretty much, right? But in terms of graph theory, there is a huge difference between these two. So maximal is a clique that is not a subset of a larger clique. So this is like a locally largest clique. So you cannot expand it by adding extra vertices, right? So let's say if you look at your Facebook network or something, there may be a bunch of cliques in your local networks, right? So there can be a clique of classmates that you had in high school, and then there is a clique of college friends, right? So when you try to look at these different groups, you're trying, like you found one, let's say, right? And you're trying to expand the group to see if you can make it larger by adding extra friends to it. If there are no friends that qualify, then you say, okay, it's the best I can do locally, so it's a maximal clique, right? So, and then the maximum is the largest one in the graph. So this would be your largest group of friends, such that not only you cannot expand it locally, but there is no other clique in your network that is larger, all right? And omega of G is used to denote the clique number of G, which is the cardinality of the largest clique in the graph, all right? So this is the number of vertices in your largest clique, so you denote it by omega of G. Difference between maximal and maximum is important to remember, because if I'm talking about computing a maximal clique, That's actually a trivial problem. Because yeah, you can solve it easily algorithmically by just start with a random vertex, add a neighbor, remove all non-neighbors, and keep doing it until you reach the point where there are no more candidate vertices to add, right? So at that point you can claim that the clique is maximal because every vertex from outside has at least one non-neighbor inside. So it cannot be expanded any further. But if you want to find the very largest one in the graph, then this approach is not going to work. So it's actually a really maximum clique problem is really tough. Much harder problem to solve. Some etymology, the term clique comes from French, meaning a noise. The definition of WorldNet dictionary, an exclusive group of people with a common purpose. Now, the term was introduced to social network analysis first in 1949, even though complete graphs were studied in graph theory long before. But the term clique came from social network literature. In 1949 was introduced by two graduate students from MIT. This paper, they used the term clique for the first time to describe the set of nodes of a complete graph, essentially. And then, since then, this term has been used everywhere. Speaking of influence of social network analysis on other fields. So now it's a common term in mathematics, computer science, operations research, and used very broadly to represent the set of nodes of a complete graph. And sometimes, actually, they use this term interchangeably with complete graphs. So sometimes when they say clique, they mean the graph, but the actual rigorous definition of a clique is a set of vertices rather than the whole graph. A very closely related concept of a clique is the independent set. So this is like the complement of a clique. They're so close to each other that essentially from optimization perspective, this is the same problem, because if I look at my original graph G here and my complement graph G bar, then an independent set is a set of pairwise non-adjacent vertices. A clique is a set of pairwise adjacent vertices, right? So if I look at the complement, whenever I have a clique in this network, I'll have an independent set in this one and vice versa. So you have this one-to-one correspondence. So let's say here, to illustrate the concepts like 1, 2, 3 here, right? So it's a clique, and it's a maximal clique actually, because if I try to add vertices from outside, like 4 has 2 as non-neighbor, 5 has 2 as non-neighbor, so neither 4 nor 5 can be added. So it's a maximal clique, right? And this corresponds to a maximal independent set in this graph here. 2, 5 is an independent set on 2 vertices. 2, 5 is a clique on 2 vertices here. So, but the largest clique in this network would be this one consisting of 4 vertices, 1, 3, 4, 5, and this is your maximum clique, and this one corresponds to the maximum independent set. So the omega of G in this case is 4, and then guess what's the name for the independence number, which is the cardinality of the largest independent set. So omega for clique. What would you use if you know the Greek alphabet? Omega is the last letter of Greek alphabet, right? Everything is there. Clique, all the edges are there. So no edges are there, you would use what? Alpha. Yeah. So alpha of G is the independence number, usually. So from alpha to omega you go. When we solve the maximum clique problem, this is just to find the cardinality of the largest clique in the graph and to find the largest clique in the graph, actually. But sometimes we may have different objectives. So one common one would be, so let's say you have the weights associated with vertices and you want to find a clique of maximum weight. So this is the vertex-weighted version of maximum clique. So here is another version where you have the edge-weighted clique, maximum edge-weighted clique problem. In this case, you have edge weights associated with all the edges, and then you are trying to find a clique of the maximum total weight, right? So let's say here is a large clique with 5 vertices. So there are a total of 10 edges here, so the total weight would be 10 here. Here you have just one edge, so a clique of cardinality 2 that has a higher weight. So this is a better solution than this. And then there you have a clique of edge weight of 12, which is the best one that appears in this network. That could be something that could be a reasonable objective in some applications. This is just to show that we'll not only look at cliques of large cardinality, but sometimes you'll have different objectives, okay? And we'll discuss this later. So now, clique is great and all perfect, but sometimes perfect means unrealistic or impractical. Now, this illustration here shows a bunch of protein complexes, and none of them is a clique, obviously, right? So this artificially generated graph, which has two clearly defined clusters here. So if you ask a child what are the clusters here, they'll tell you there are obviously two, right? None of them is a clique, so there are some missing edges there. Even if your actual cluster that you're looking for is a clique, you may have some missing data that doesn't allow you to see that the edge indeed exists. So let's say in these protein interaction networks, the edges are built based on biological experiment, which is not 100% precise, so you may miss some of the connections, right? So as a result, what in reality is a clique doesn't look like it in your network representation because of the noisy data, right? There is this issue, noisy data is one, and then on the other hand, sometimes the structures of interest, they are not cliques to begin with. They're something else. Like these protein complexes, again, they're very meaningful protein complexes biologically. They're the actual clusters that we are interested in, but none of them is a clique, right? But then if you look carefully, maybe they do have some elements of a clique. And let's see what people try to do in order to address this issue. Clique is essentially too perfect to be realistic, right? So people responded to this by introducing a bunch of other concepts. And typically the way it happened, if you look at the literature discussing different types of clusters, usually these are essentially ad hoc efforts. So usually there are some researchers who are interested in a particular application. And what they do, they introduce a certain concept that is of interest for that particular application. They define it and then maybe design some simple algorithms or show some examples illustrating the concept in a simple graph. And then there were like a bunch of these concepts that were introduced in the literature. So I'm going to go over some of them just to show you how many of them are out there. And not just that, but these concepts are actually something that we'll be interested in. Lewis in 1950 introduced the concept of the so-called s-clique now. I would call it actually distance s-clique. The set of vertices is going to be called an s-clique if the distance between any two vertices in the set is no more than s. Essentially, we relax the distance. In a clique, the distance is always 1 between any pair of vertices. Here we allow it to be larger than 1, but no more than s, and s is usually something small, maybe like 2, 3. In airline networks, you would probably want to design an airline network where s is no more than 3 for sure, right? So you don't want to make more than 2 connections when you fly. Here is an illustration of a 3-clique. Here the distance between 1 and 6 is 3, and this is the largest distance you see in this graph. Now, if I focus on this cycle, then the highest distance is going to be 2, so it's going to be a 2-clique now, right? So if I look at 2, 3, 4, 5, 6, it is still a 2-clique because the distance between any two vertices is at most 2 here, right? But the distance between 2 and 5 is actually 3 in the induced subgraph. If I restricted my group to just these nodes and removed the 1, the distance would become 3. But the distance is 2 in the original graph because you have this outside vertex, so they're connected through an outsider, right? Doesn't look like a very cohesive group. You have to use outsiders to make sure that you are within the group. So that's a weak point of this definition, and this was addressed some years after by introducing this concept of S-club now. In S-club, we require the diameter of the induced subgraph to be no more than S. So see here again, we are looking at the largest pairwise distance to be no more than S, but we are looking at induced subgraph now. We cannot use outsiders because we restrict ourselves to induced subgraph now. So like before, we have the whole thing is a 3 club, 1, 2, 3, 4, 5 is a 2 club, 2 clique that we considered before is a 2 clique, but it's not a 2 club because we cannot use outsiders anymore. In the induced subgraph, the distance between 2 and 5 increases to 3. So then another alternative in the concept of s-plex introduced by Seidman and Foster, we allow to have no more than s non-neighbors within the group. No more than s non-neighbors, including the vertex itself. So if I look at one plex, it's the same thing as clique because the only non-neighbor I have is me, myself, right? So I'm neighbor to everybody else. This kind of relaxes your familiarity restriction. You don't have to be familiar with everybody, but you can have at most S members of the group you're not familiar with. Another concept is that of s-defective clique. S-defective clique allows to have at most S missing edges within the group. Clique doesn't allow any s-defective clique, so you have S defects, meaning that you can have up to S missing edges, which is actually even more cohesive than s-plex. And then the next concept that was considered in the literature that is very popular is a K-core. A K-core requires that the minimum degree of vertex is at least K. Then K-block requires that the connectivity of the induced subgraph is at least K, which means that this is a reasonably robust structure. You can remove up to K vertices without destroying the connectivity. So then gamma quasi-clique was the concept introduced based on the edge density. So the edge density of the clique is perfect 1. If you allow it to be slightly less than 1, but at least gamma, then this is what we call a gamma quasi-clique. So this is a very dense graph. Another alternative, lambda gamma quasi-clique. This one goes a step further and requires not only the edge density of gamma, but it requires also that every vertex connects to at least lambda% of the potential neighbors within the group. Because in quasi-clique, like the overall density can be high, but then you may have some vertices that have very few neighbors still, right? So this eliminates that. Say we require to have at least 60% of potential neighbors must be actual neighbors, and then the overall edge density must be at least 70%. Now, if you summarize, we kind of went over this really fast. You didn't really have an opportunity to appreciate what these concepts are all about, but at this point, my goal was to just illustrate that there are so many of these clique relaxations there that were introduced in an ad hoc fashion. This is of high practical interest, and there was a lot of work done on the topic. Here I list them all together just to show that this is your cluster jungle here, right? So that like when you start looking at it, if you are confused about all these definitions, that's exactly the effect I wanted to have at this point. You have this jungle, and if I'm doing cluster analysis, so where do I go? Which cluster should I study, right? And then the next time we are going to introduce the order in this jungle. Okay, so we'll have a systematic framework which will analyze all of this and will put it in an organized, systematic fashion, which will be easier to understand, and you'll see how many great things we can do by just analyzing things in a systematic fashion.